Welcome to Secure Software Development. Let's get started by the same standards we always apply when we're starting off, talking about web browsers. Remember cross-origin resource sharing? We've talked about it before and here a couple of times. And this is something that's essential to making the world work. And examples are right there. You might have a style sheet that you go get from where you go and you get some stuff from Google. In this case, we're going and getting a font. It's a font Sophia. Or maybe we want some icons. We can go and get Google's material icons, and then they're available for me to use in my web page. And number of different ways to do that. So maybe you need a font. Great. You reach out to Google and you get your font. No problem. Maybe you need an image. So you want to reach out to apparently Google also. Okay. So you reach out to Google, get your image. You might need a library to implement your website, which apparently also comes from Google. Fine. But maybe you need to authenticate. You want to authenticate a user. So you might use Google's authentication mechanism to do that as well. Oh my goodness. Okay, this is getting out of hand. Let's just go on. So the point is that we need to be able to have some cross-site requests. So, for example, we might load a page from netacurl.de, and it may reference other items that are available at the same domain. And it might do so by using an embedded element or by a fetch or by an or by an XML HTTP request. There, I got it out. If it's the same origin, I talked about this back in the privacy discussion, hostname, protocol, and port. If it's the same origin, we allow it, right? You're reaching, a website is reaching back to its own site to get data, and we allow that. Reaching to a different host, that's a little suspect. Using a different protocol, maybe that's a little suspect. Using a different port, that could be a little suspect too. But if it's the same origin, we allow it. Different origin? Well, it becomes a cross-origin request. And it might be allowed or it might not. We need a set of standards to help us decide. So, for instance, connections to minehouse.de are permitted, but connections to Shadasoft might not be. So we may have some connections we permit, other connections that we don't, even though they may only differ by port or by protocol or by hostname. What about your local network? Well, web pages run code. How many times I have to emphasize that? I used to get kind of irritated when people were building a web page and I'm coding and they're slinging HTML. I'm like, coding? You're writing HTML. At best you're writing a document. But the sad fact is web pages, they're code. So yeah, you're coding. And because of this, sometimes you have stuff like a web page that port scans your local network. And that's not necessarily a bad thing. That can be done because a company like Samsung has a lot of different devices. It wants to help you set them up. So you visit a web page. That web page runs a port scan to find Samsung devices on your local network and let you configure them. But is it possible to use port scanning for nefarious purposes? Okay, that's just dripping with sarcasm. Of course, this is a problem. So Google created something to address this. They created a standard. I told you before, when you have something like this where it's not being addressed, one of the best things that you can do is create a standard, even if it's just your own internal standard. Say, this is how we are going to consistently, across our entire software product, or maybe across our entire software product domain, this is how we're going to deal with this. And Google created a standard for it called Private Network Access, or PNA. It's a standard. You can go read it at that link. Great. Now, what does it do? The purpose of PNA is to prevent your web browser from hosting attacks on your local network. Right? What would that look like? attacking your local router. Sometimes a router will allow connections from a host that has an IP it assigned. Right? It assumes, oh, you're inside the perimeter, therefore you're okay. All right, we're getting away from that with zero trust, but you can see what happens, right? Sometimes you're not allowed to to connect to your router and configure it from outside the network. You can only do it when you have a network address that's inside your network, assigned by your router, and the web browser is running on your machine that presumably has an address assigned by your router. You could attack web interfaces on your local machine. Are there web interfaces on your local machine? You're probably running software on your local machine that may have a web interface to it. Weirdly enough, some antivirus stuff and those sorts of things, they provide a web interface. That's how you configure them. And that's true for some other tools as well, right? You open up the tool to configure, and in reality, what you're doing is the interface is actually a web browser pointing to a local interface. You might have, again, it's just code. It might run its own service. It might say, hey, here I am. I'm advertising my own service running in your browser, but I'm also advertising an interface on your machine. Those are bad things, or they can be bad things. They can be used for good. They can be used for bad. But, the potential of using them for bad is pretty high, so maybe we shouldn't do it. Can you really attack routers this way? Sure. 1, you can determine the local IP address of the host machine from inside a script. 192.168.1.1.214. Okay, once I know that, I can guess what your router IP is. It's probably 192.168.1.1. So once I've guessed it, right, we're in the router's IP space, maybe we can change settings. If the router is not protected by a password, and sometimes it's not, or if I know that it was installed by a certain ISP and I know the protocol they use for assigning passwords. And yes, one of our houses, the password was something to do with our street address. It was not great. And if you didn't change it, it would have stayed that. So once I know that, it can be directly attacked by a simple HTTP request. So we could check for the router with a little script request, right? Either that's going to work or it's not, and we can see whether it worked or not, and then we can take action based on that. And potentially, if I know some stuff, like I know the default username and password, default username, let's say is admin, default password is admin123. I don't know if you knew that, but you can build those into a URL. You can build a username and password into a URL. That bottom URL will let me connect directly to the router and change the DNS to point to another location. It changed it to point to a 555 location because we're in a movie. That's a joke that maybe only Americans will get. Sorry. So there you go. Arbitrary command execution? Yes. I mentioned before that some software on your machine may set up an endpoint used for configuration. Trend Micro, for example, installs its own password manager, right? You download the Trend Micro antivirus. It installs a password manager for you. How convenient. The password manager is automatically launched on startup. It wouldn't be any good if it weren't, so it launches it on startup. So now it's running. The password manager is written in JavaScript for Node.js because everything is written in JavaScript for Node.js or Electron, or it's just, this is how you build applications. And it has multiple HTTP RPC, remote procedure call ports, for handling API requests. One of which opens a URL in the default browser. Now that makes sense, right? If you've used a password manager often, from within the password manager, you can say, I want to launch this site. It needs to be able to tell the default browser to open up and go to this URL. So it has one for that. The way that Trend Micro does it is using something called shell execute. Shell execute runs arbitrary commands. So hooray! So for example, I could create an XML HTTP request, and then I could just point myself to localhost to the correct port for the Trend Micro Password Manager. I could tell it I want to use the open URL in default browser endpoint, and I give it a URL of running command.exe. That's not great, right? So that's not ideal. It's probably better things that you could do than that. Fortunately, I can't read the reply from the script because of cross-domain restrictions, but at some point you don't care because you're able to encode everything you want into the request that you're sending. Right? So if you want to see about this particular little problem, you can read the report and replies about it at that link. So, Google solved this problem. They solved it. Recently solved it, 26 September of this year. Finally, we can't do the things I was just telling you that we were doing. Distinguish public, private, and local networks. Right? They need to be handled differently. Public networks, fine. Private networks, it's a little different. Local networks, still a little different. You got to think about how you're going to do that. Pages loaded under a less secure context, like a remote website, right, will not be able to communicate with more secure, from your point of view, that's private IP or local IP contexts, okay? And that's great because that prevents contacting localhost or prevents contacting your router on your private IP address, etc. So the first one is a local address, it's your local host. Second one is a private IP address because it's your own personal, non-routable private IP space. We're going to prevent those. And that makes us secure forever. And it's a standard, so people can go, they can grab this, and they can implement private network access, and we can all be more secure and safer, and everything is great. And that's how standards work. The problem is now solved. So what is that? 0.0.0.0. Is that a valid IP address? It's 4 octets, so I guess it is. What is that point? Is that a broadcast address? What is that? Well, according to RFC 1122, it's special. And it refers to this host on this network. Okay. It must not be sent, out on packets, except as a source address as part of an initialization procedure in which the host learns its own IP address, right? Initially, I don't know my IP address. It could be anything. So I need to reach out to someone. I need to ping somebody, something. Let's see, broadcast to the world. Give me an IP. And so maybe what I do is I just let my current address be zeros. And great, they'll respond, and then from then on, I'll use that address. So that's interesting. But then it says, see also section 336 for a non-standard use. And it can be used in some cases. It may be used as the broadcast address. So that's possible too. So that's interesting. So 0000 is actually kind of localhost. This host on this network. So really, I could think of it as 127.0.0.1 or localhost. Let's try it. So if I ping 127.0.0.1, boom, it works. What if I ping 0.0.0.0? Look at that. It pings 127.0.0.1. So, wow, it really is pointing to localhost. Now, you remember way, way, way back in the past, I mentioned, in the talk about complexity, I mentioned this 18-year-old bug in Mozilla's Bugzilla report. 18 years ago. So, in 7 August of 2024, Oligo Security Tests, they started testing their implementation of Google's PNA. You may say 7 August, but that other thing said September. It's been updated. Just bear with me. So 7 August, right? Everybody knows what's going to go on. They're going to try to test this. They're checking it out. And they discover that Google didn't account for 0000, and as a result, I can reach out to localhost using 0000, and private network access does not block me. And so it turns out the issue, let's go back a page, the issue back here was actually a security issue. Was it a bug? Still not sure, but definitely a vulnerability, an exploitable vulnerability. So, would you like to know more? I mean a lot more. Would you like to be able to use this little fact that 0000 is localhost? Would you like to be able to use that to attack AI workloads remotely? You would? Great. Shadow Array campaign is what you want to look into, and there's a great report at that link that you can go and read about. Finally, a use for 0000. So what are the implications for development from this? Well, even when there are specifications, and you've taken pains to document the behavior, understanding and accounting for everything, all the behavior of a computer system is hard. It's hard. Before this, did you know that 0000 was localhost? How would you have known it? Why would you have known that? And if you knew that, why did you know that, right? Design choices that are made in connected systems can expose you to vulnerabilities even when you have a carefully designed specification. The people at Google aren't dumb. They're not morons, right? They know how to do internet specifications. It's Google. And they still, got this one wrong and left a big vulnerability. Whew. So let's talk a little bit about developing software. There are some essential principles, and we're going to go over 3 of them here. And one of them, the first principle we'll talk about, is establish secure defaults. You're going to develop some software. At some point, that software will be deployed. Somebody will, download it and install it, or they'll clone a repository and build it, or they'll do something to set it up and start it running. And ideally, once they've done that, they are in a secure state. That's important. There are quite a few CWEs that deal with initialization to an insecure state. That's bad. If the system as it comes out of the box is insecure, in many cases it will stay insecure. You need to help the user by making sure they deploy the system into a secure state. I don't know how many times I've installed some web app or something in a directory, and there's a file there that happens to have the name security, and I'm like, should I read that? And I go and read it, and it's like, oh, by the way, nothing is secure. Do the following 20 things to secure this, and then I've got to go do a whole bunch of stuff. Why not just have a script that runs as part of the install or part of the setup that does that for me? Lots of other tools that I use do that. You should do that as well. The whipping child for this one is MongoDB. MongoDB has had many instances, dating back to 2014, of insecure default settings. For example, default configuration of MongoDB, widely used, did not require authentication for connections. So you're like, I'm just installing it locally as a local database. It will run locally. Well, you know what? It's got an internet connection to it, and you forgot to lock that down so people can just connect to your little local database and do whatever they want. That's not good. Okay? And this has led to a bunch of ransomware attacks over the years. You can read all about that. Second, minimize the attack surface. When we talked about the black box project, that little case study that we did, everything in that was geared toward minimizing the attack surface. It was all in service of minimizing the attack surface. Bunch of CWEs deal with that. The one that's sort of obvious is 1125, which is excessive attack surface. Look, every feature, every library, every capability or configuration that you add to your software increases the attack surface of your program. One rule of thumb, maybe it's a little bit draconian, but one rule of thumb is if you or your customer don't need something, consider turning it off, at least by default, or maybe even removing it. Or if you're developing a new system, don't put it in, okay? The stuff that's in there can be exploited if there's some feature that you want to put into the system. And it's not quite 100% yet. Maybe at the very least gate that feature so that it's off by default. The one I keep picking on, I've picked on this throughout the class, and I'm sure I'll pick on it a few more times before we're done. Even though we're close to the end, there's still plenty of opportunity to pick on it, is SMB, the Server Message Block Protocol. This was designed back in 1983 for networking IBM DOS computers and was later used in OS/2. SMB1 was published by Microsoft in 1996, so 13 years later, as the Common Internet File System, CIFS, and it was compatible with the earliest versions of SMB. So reaching back all the way back to 1983, right? All the way back there. SMB1 was deprecated by Microsoft in 2013 and was finally removed as a default install. You can still install it, but it's not there by default in 2016. Okay, it's not there, right? So 2016 it's gone. No, it's removed as a default install, but you might have already installed Windows and it might be there. And so it just persists. Or you know, any number of things could have happened. It was used in the Sony Pictures hack in 2014. WannaCry used it in 2017. SMB Ghost 2020. SM Bleed in 2020. And there are lots and lots and lots of others. So Microsoft has published a technical note in 2019 about SMB. You can have a look at that. Basically, this is the gift that just keeps on giving. It just will not go away. And it's constantly a source of vulnerabilities in Windows. Minimize the attack surface. Get rid of this thing. You don't need it, right? You're not trying to network a PC in the 1980s, right? You're not building, what was that car? KITT. You're not building that car for Michael Knight from Knight Rider. You're not doing that. Get rid of it. And 3, fail securely. When failure is detected, put the system in a secure state, or make sure the system fails into a secure state. Again, that was something that showed up in the discussion of black box. The failure mode was we just delete everything and we kill power and everything burns down and blows up. Fine, that's our safe state, because the problem we had was the potential for data loss. The way you don't lose data is you immediately grind all the data, shred all the data. When failure is detected, place the system in a secure state, right? Make sure that if there's sensitive data in memory, you erase it. You can do that in the exception handler, right? An exception occurs when someone's entering sensitive information. Don't just handle that exception and populate it up. That stuff is left in memory. Erase it. So make sure there's a known safe state. Figure out what that looks like for your software. Explicitly set those conditions. Set up the local variables, make sure everything's erased or cleared or whatever whenever you detect a failure. It's not easy, but if you want to be secure, that's what you need to do. Examples of this, remember the Apple GoToFail vulnerability? It's an example of this, right? We connect and we have a failure, so we just default to connection. Everything's fine. We just let you go ahead and connect. That's bad. MySQL had a very similar vulnerability. There's a CWE for this, not failing securely or failing open. That's bad. It's bad, right? You don't want to do that. So the 3 important principles that you should keep in mind, okay? Secure default install, right? Set things up so they are secure from the get-go. That means you got to pester the user with questions to configure stuff, do that. But make it secure out of the box. Minimize the attack surface. If you don't need it, turn it off. Get rid of it. Whatever. Minimize the attack surface. And fail securely. When a failure is detected, get yourself to a secure state. Don't leave sensitive data lying around. Don't leave connections open. Get yourself to a secure state. You do those things, you've actually covered most of the stuff you really need to do. Let's talk about program analysis. Now, we've talked about this a little bit in the past, but basically program analysis is the process of posing and then hopefully automatically answering questions about software. And we can do program analysis with assembly code or with machine code or with source code, right? It just depends. Sometimes you might have a specification. Sometimes you might have a set of contracts. There's a number of different ways we can do this and a number of different artifacts we can use to do it. The questions can be about correctness. They can be about optimization, and they can be about security, right? Or any other thing. So program analysis is just our way of analyzing a program to answer questions. A question might be, what does this program print for the input 19? How would you find out? That first line there with the MK, that's a make line. It just tells you that to build this, we need to use GCC. Don't worry about it. It actually is part of a tool that we use in the reverse engineering class. It's not important here. So there's some C code. That C code does some stuff. One of the things it does is use scanf to read a number. By the way, using scanf to read a value is a bad idea. Don't do it. There are much more secure ways to read from the console that actually check the number of bytes read. So, how would you find out what it does? Well, one way would be to compile that code and run it. Seems easy to me. We'll enter 19 and we'll see what we get. And what we get is, when we run it, we enter 19, we get an output of 20. So this code, when it's run with an input of 19, one of the things that it might do is print 20. Now, notice I said one of the things it might do. What else might it do? It might tell us it's built for the wrong architecture. It might tell us it's out of memory, right? There's a lot of different things it might do, but we know that one of the things that it might do is tell us 20. So we know a potential result for this. We can call this dynamic analysis because we ran the code, right? We don't want to say, well, I ran the code and checked it. We want to sound like we're erudite people with advanced degrees in computer science, and so we say, I did dynamic analysis on this program and determined that for an input of 19, it yields an output of 20 in some cases. Wow, okay, that sounds smart, but it's really just, I ran the program. So how about this question? For what inputs, if any, does the program output 0? Well, we could again run it, and we could try different inputs and see if we get 0, and we might get lucky and get 1. But the question has this sort of for all nature to it. It says, for what inputs does the program output 0? So that sort of seems like I want to know them all. And that might be tricky. I guess, right, that scanf is reading a 32-bit unsigned integer. I could just try them all. How many could there be? Well, 32 bits. That's 4 times 2 to the 30th. 2 to the 10th is about 10 to the 3rd. So that's about, 4 billion possibilities? So it's a lot. It might take me a while to do all that. Just running it and randomly sampling, we might get lucky, we might not. We could just read the code. Let's try that. Let's just read the code and see if we can figure it out. There's not a lot of code there. We're smart, right? We got computer science degrees or whatever. We know what we're doing. So look right there. There's the output line. It says printf, That's our tip-off that it's an output. And we print out a 32-bit unsigned integer. That's what that pre-U32 is. I'm assuming you know what int types.h is, and you're aware that you should be using those, but just in case you're not, that's a macro that resolves to the correct code for printing out an unsigned 32-bit integer. And above you see uint32_t. That's the correct type for a 32-bit integer. You should be using those types. Avoid int when you can. Anyway, we're printing out a number here, and we're printing out count. So the output's going to be count. So we care about anything that deals with count. Oh, look up at the top. Count is set to 0. That's what we care about. We care about count being 0. We set it to 0, and then we print it. That sounds great. That means okay, it's changed. Every time we go through that loop, we add 1 to it. So we start out at 0. We might add something to it if it goes through that loop, and it won't be 0 anymore. And then we print it out. So what can we say about when it's 0? Well, if that loop never runs, then count is never incremented, and count stays 0. So the loop only runs when number is greater than 1. So if number is less than or equal to 1, that loop won't run, and count will be 0. So if I enter a value of, and it has to be an unsigned 32-bit value, the only ones that are less than or equal to 1 are 0 and 1. So if I enter 0 or 1, I get an output of 0. I got them all. I solved it. I am so smart. There we go. Right? We figured it out by examining the code. Now, saying I read the program and figured it out, no, come on, anyone can do that. You are a computer science student. You are an upper division. You're a graduate student in computer science. We did static analysis of this program, right? Which means we looked at the program. There you go. And typically with static analysis, right? Static analysis is different from the dynamic analysis because I don't run the code, right? I read the code. And with dynamic analysis, I run the code. Two different things. We could never mix those two things. Right. We do. For dynamic analysis, we know something. We know something with certainty. We know what the code does for the given inputs and for the environment for that particular run. I know what's possible for the code to do. This works well for code that's safe to execute, right? I'm like, I wonder what this virus does. Let me run it. No, don't do that. Don't do that unless you're in a nice, well-contained sandbox, right? We need to, and maybe the code doesn't run in a reasonable time, right? Maybe it takes a week for the code to run. And I don't have time to run a bunch of experiments on that, so maybe I need to actually read the code instead of trying to run it. But often it's fairly simple to set it up. Now, it's complicated by the fact that ideally I will do this with correct experimental control around the program. That is, I will have thought through what the program environment needs to be, how it's going to run, and what could be different from one run to the next. What are my external sources of variation in my experiment? It's an experiment. Maybe you don't think of it that way, but you should. When I run it, sometimes, and you know this, right? Sometimes when you run a piece of code, it behaves differently. Sometimes when you try to start up a program you've been starting up on your PC, it behaves differently. Sometimes when you choose an option in your program, it behaves differently. Right now, I'm being driven nuts by an Adobe program because after it's been running for a while, the menus stop working. Okay, right? What is that? Right? I'm doing the same thing I did before, but I'm getting different results. That's because there is an external source of variation, memory leak, whatever, I don't know. Something that is causing it to behave a little differently. But if I establish experimental controls around that, then I can say something about the result. And there's a whole science of doing that. For static analysis, we can know with certainty what the code does given our assumptions about it. I'm going to beat on this for most of the rest of this particular lecture. This works well for code that is not safe to execute. viruses that might not run in a reasonable time and for which we want an ever or any answer, right? We want to know all of the results, which is true. We want to know, does it ever do this? Does it do this for any input, right? And that can be hard. Static analysis can be hard. It requires that you read code. That's tough. And I can write the stuff, but making me read it, that seems cruel. And this is, it says this is what most of us do in this class. This was slides built for the reverse engineering class. Don't panic. We're not going to spend a lot of time in here doing that. But doing static analysis properly requires a model of the computation, right? Doing it correctly requires some additional thing. For dynamic analysis, it's an experiment, and I need experimental control. For static analysis, I'm evaluating it given a model about the program, and that model can be better or worse. George Box said, all models are wrong, but some models are useful. Hopefully, we have a useful model of the computation. We don't have the perfect true model, because the perfect true one is just what the code does when you run it, and we're trying to figure that out. So at best, we have an approximation to it, but hopefully it's a useful approximation. Hope this makes sense. Experiments versus models. All right, dynamic analysis is an experiment, static analysis is built a model. Both require some discipline so the results are useful. And neither is the program itself. You do the experiment, you see one set of outcomes. You build a model and analyze it in that, and you predict another set of outcomes. And then you run it and something else happens. It's entirely possible, right? The world is a complicated, weird place. Maybe you discover a bug in the processor or a bug in the library, and you didn't see it during experimentation. You didn't include the bug in your model because how'd you know about it? And when you run it, you see something different. So it's entirely possible that you get a different result. Keep all that in mind. All these things are imperfect. Given all that, let's think about the full range of behavior of the piece of code we just looked at. So here's what we said. We looked at this code, we read it, and because we have big brains, we said, okay, it outputs a 0 when the input is less than or equal to 1, and that is the input is either 0 or 1. Now, was that too precise? Was it unnecessarily precise? Or maybe it wasn't precise enough. I mean, there's some assumptions in that statement. There's some assumptions about the code. There's a model that we've built up in our head about what this code means. Is that model true? Is it correct? Well, one thing we said is the input's an unsigned integer. Well, what if the input is not an unsigned integer, right? What's to stop me from typing -5 or Fred as the input? Well, if you look at the scanf statement over there on the right, you'll see that we check the return value because we're good programmers. And if it's less than 0, we fail and return a -1 because we're good programmers, right? We check to see if the return value is correct. And we told scanf we wanted an unsigned 32-bit integer. So presumably, right, scanf will give us an error if that's not what we give it, and we'll report that error back. Sounds like we've covered these cases. Let's try it. So we try it, we enter -12, and it tells us 224. We enter Fred, and it tells us 156. Okay, so wait just a minute. How did that work? How did that work? We passed a pointer to number, and number is explicitly an unsigned 32-bit integer, and we told scanf it was an unsigned 32-bit integer. So when I put a negative number in, why does it take that? What does that mean? And I put Fred in. I got 156. How does... You're looking at the whole program. The whole program. What in there tells me that the response to Fred should be 156? How does that happen? I mean, we did everything we're supposed to do. Well, what do you do when something goes wrong in your program? And I know what you do. I know what you do because you leave the stuff in when you turn your programs in. Well, you don't, but I teach classes that involve turning in programs. This is what we'll do. you add a bunch of printf statements. Or if it's C, you add a bunch of C out stuff, etc. You add a bunch of print statements to your code. So let's add a print statement to our code, and we'll check the result of scanf. Let's print out the input we get back after that scanf line that we see highlighted there. So we'll add that line right there. We'll print the result. We'll print out number. And so when I enter minus 12, I get that big number. What is that number? That is 23. That is, what is it? That is 4,294,967,284, which is not quite the same as negative 12, right? Those differ by, to me, a significant factor. So that's not right. What about when I enter Fred? Fred resolves to 427,243,168. What in that program? Again, you see the whole program. What in that program maps Fred to that number? How do you get from Fred to that number? Scanf has to do it. Scanf is saying, oh, you put in Fred, you must have meant 427,243,168. What? Well, wait a minute. Something funny just happened here. When I put in Fred before, let's go back a slide. When I put in Fred before, I got an answer of 156. For negative 12, I got 224. For Fred, I got 156. Here, I ran it again. Negative 12, I again get 224. That didn't change. But for Fred, I got 96. I got a different value. Now, wait a minute. Is there anything in this code that has a random number generator? If there were, I guess it would have to be scanf. So where are those numbers coming from? So, okay, this is a mess. So why am I? So a lot of questions, right? Questions are beginning to pile up. But let's ask the first one. Why isn't scanf giving me an error? That's sort of the root of all this, right? I expect scanf to return an error, and it doesn't. If we can answer that question, maybe we can get to the rest. Okay? So why isn't the scanf checking? If we go and read the documentation for scanf and not just use our intuition, we'll find out that scanf only reports an error when it reads an end of file with nothing else. So if I run it and I just immediately push Control D, I guess Control Z if you're on Windows, I get 255. What is that? I said return negative 1. It returns negative 1 and 255. All right, those are the same in a 8-bit domain. All right, fine. I believe that. Life is good. Whatever. Okay, so it only returns an error when it reads Control D or it reads the end of file at start. It doesn't read anything. Then it returns a negative number. What does it normally return? It returns a number. Otherwise, it reports the number of arguments read. So if I read one argument, I read one unsigned 32-bit integer, it'll return 1. 1 is not less than 0, so that didn't fail. What if it returns 0? What if it can't read 1? I mean, Fred wasn't a number. What if it couldn't read anything when I put in Fred? It would return 0. 0 is not less than 0, so that does not catch that error. Oh. So look up above there. Number is not initialized. So what's in memory right there? Well, depending on how you compiled it, some compilers will give you an option of zeroing out things when they're otherwise not initialized. But here we haven't initialized it, so it's whatever happened to be at that location, in this case on the stack, when the code was run. Whatever was there. Probably some random garbage left over from other work. So that's what number is. It's uninitialized. which leads to undefined behavior. You've always been told that like an uninitialized can lead to undefined behavior, and here we have it. So that explains why we're getting what seem to be random numbers back when we enter Fred. Scanf is running. It's not being able to read a number, so it's reporting back 0. That doesn't cause it to stop there. And then we report number, which has been left at whatever garbage was in memory before. I thought, that kind of explains what happens with Fred, right? We're making some assumptions here, but they seem reasonable. What about minus 12? What the hell is happening with minus 12, right? Because again, we get the same result back for minus 12, at least those 2 times we ran it, we got the same result back. That implies it's doing something. So, what does it do with minus 12? Well, let's stop for a minute and let's think about program analysis more generically. We'll come back to the program in a minute and figure things out. But for right now, think about it more generally. I've got a program, and there are inputs I know about, and there are outputs I see. But there can also be inputs I don't know about and outputs I don't see. Can there be? Of course there can't be. I mean, think about playing a game. Think about playing an online game. Other players are making moves or doing things, and in certain kinds of games, I see those, right? Like if I'm playing chess with someone, I'll see their move. But in other types of games, for example, I might be playing a combat game, and a character is hiding, and I don't know that the other player is hiding. I can't see where they are. And so there are inputs to the system that are going on that I don't know about, and there are outputs of the system that I can't see, and that's by design. Well, I'm intended to have imperfect information because that's what makes the game fun in that case. In chess, I have a perfect information game, and it's fun for other reasons. So, in addition, just running a program, it's going to reach out and get information from the processor, from the file system, from the network. And a lot of that, I don't see those things happen. I don't see the outputs, maybe requests that go out to the network, and inputs, data coming back from the network. I don't see that. And so the behavior certainly depends on that stuff, but I don't necessarily see all of it. When we run a program for dynamic analysis, we have to establish experimental control. We need to be able to say, these are the inputs I can control, like the input number, and these are the inputs that I cannot control, like the initial state of memory. I also need to understand which outputs are observable, like that response that we see coming back. And it would be great to know which are unobservable, and in most of these, there was an exit value, but we didn't see it. We just looked for it in that one case, but otherwise we didn't bother to look for it. So, it's important for experimental design, dynamic analysis, to be able to classify and understand that there are controlled and uncontrolled factors in your experiment. Same thing is true for static analysis. When we analyze a program, we have to establish a control boundary. We still have to identify the controlled inputs and the uncontrolled inputs, like the initial state of memory. These all feed into our model in some way, right? Our model depends on the number you enter, but it might also depend on the initial state of memory. If I wanted to tell you what it's going to give me back when I enter Fred, and I also model the initial state of memory, I might be able to answer that question, give you a correct answer, correctly predict what it's going to give you. If I don't model it, then I'm open to surprise. Okay? For static analysis, we need to consider cases where the system may exhibit undefined behavior, right? And that can be because there are inputs we don't know about and there are outputs we don't see. So, right, we enter something that's not an unsigned integer, then the output is unspecified. Let me try to fix the program to account for this. But let's take a look at scanf, right? Scanf returns the number of items successfully read, which is going to be 1 when the program behaves the way we expect it to. And so we could modify that check. Instead of saying less than 0, we could say less than 1, and that would catch it, right? Because the return value of 0 is actually indicating an error to us. Okay, so that's one possible fix. But this raises one of the questions we've already asked, which was, what if I enter something that's out of the 32-bit unsigned integer range? And that could be like a -12. That's outside the 32-bit unsigned integer range. Or something that maybe exceeds that range, something that's too big to store in 32 bits. What happens in either one of those cases? What does the system do? Well, we could try it and see. 32-bit unsigned integers have values that are in that closed interval, right? And if you look at that, what is that? That's about 4 billion, right? It's 4 times 2 to the it's 2 squared times 2 to the 30th. So it's 4 times 2 to the 30th. 2 to the 10th is about 10 to the 3rd, so it's about 4 billion. So what if we enter something that's greater than that? Let's try it. So I run it and I enter that highest number. It ends with a 5. Now I put in the number ending with a 6. I add 1 to it, and it reports the 0. Scanf thinks it read a 0. That's the first thing we print. And then, of course, we run it and we get back a 0. This is another input value that yields a 0. We didn't account for this the first time with our 0 or 1, so we found another one. And we have a new assumption about what scanf does. It looks like scanf, quote, wraps around, unquote. And so we give it an input, and it gives us back the input modulo 2 to the 32. That seems reasonable to me. That explains everything we saw before. It actually explains the -12, right? Because it represents -12 as a 2's complement number, and then treat it as an unsigned number, and do it mod 32 to the 32, I probably will get that result. I'm not going to check that here in the slides, but that seems reasonable to me. So let's go with that as a working hypothesis. Seems reasonable. Is it true? I've already been burned by this little short program a couple of times. I don't know. So let's go check the documentation. And the documentation tells us nothing. Documentation for scanf is not great. It's unspecified. So since it's not specified, scanf might do anything. Well, we don't want it to do anything. We want it to do what we want it to do. So let's try some other stuff. For fun, let's try some big numbers. So 64-bit integers have values in that closed interval, which I will not try to pronounce that number. But you can figure it out, right? I mean, 64 bits, 2 to the 4th is 16. Times 2 to the 30th, times 2 to the 30th, so it's 16 billion billion. There you go. What if we enter something greater than that? So let's try, just for fun, let's try entering the limit, that limiting value. Setting something greater than that, let's enter that specific limiting value and see what we get back. What we get back is, right, so that's sort of all ones, 64 ones. What we get back is the value that's all ones for 32 bits, and that seems right. This seems to conform to our wraparound hypothesis, and our hypothesis is part of our model of the program. So our model seems to be doing pretty good. It seems to have correctly predicted that, right? I would have said, well, it's going to wrap around. We'll end up with all ones in the 32-bit field, and that's what we get. And that's what it got. So that's good. Let's experiment a little bit more. Let's try one less. Look at that. One less, right? One less in the 64-bit world was saying one less. Right? That what it does is it turns that lowest bit to a 0. And what we get back is that lowest bit set to 0 with the 32-bit field. Life is perfect. This model is working great. Let's try one more. So I seed the 64-bit field by 1, and I get that answer, which is not what I expect. That's all ones, right? The top one there is that big number is a 1 followed by 64 zeros. The bottom one is 32 ones in terms of its bit representation. That's not wrapping around. The heck is that? Okay, so my model, which said that just wraps it around in the 32-bit field, that's broken now. It's a good model while it lasted. So it doesn't wrap around. If you play around with it more, it turns out that scanf seems to parse your number and accumulate up to a 64-bit integer. And once it reaches that, it seems to perform modular arithmetic, but even that's a little bit sketchy. So this just points out that you can you make reasonable assumptions about what things do. When you really dig into it, computers are weird. They do weird stuff. And you have to understand that if you want to write secure programs. Right? If I'd written this, and this was part of some, this kind of logic was part of some big secure system, I'd probably done a bad thing, right? Because I can get weird results by putting in these odd numbers, putting in Fred, putting in -12, putting in big numbers, and I'm getting back things that don't conform to any of my expectations about what it should do. Since my expectations are wrong, my security that I build in it might also be wrong. How could I do better? Well, one thing I can do is I can try to reduce the attack surface. I can limit the domain. I can explicitly check and be sure that what I get back is something that conforms. Instead of using scanf, I can be more precise. I can actually read a certain number of characters, and I can be very, very careful with how I parse it. We did that, for example, in black box. So minimizing the variability in it, reducing the attack surface, all things we talked about. I can try to do those things to make it better. But again, I see what I see when I run it, the experiments, and when I read the code, I'm reading it with a set of assumptions about what things like scanf do, and those assumptions, that model, can be wrong. So that takes us to the more general topic of program analysis, and maybe one way around things is to not have me making a bunch of assumptions. Maybe it's better if a computer program is making assumptions for me. Wouldn't that be great? That would be great. So maybe there's a way to automate this sort of analysis. So one thing I'd like to point out, maybe this is already obvious to you from the example we just looked at, vulnerabilities often occur at the edges. And that could be where two systems meet, right? I take two systems and I connect them together. Okay? I connect, for example, I wire in my, some secure library into my code. And if I'm not careful about that interface, as we've already seen, I can wind up with vulnerabilities. We saw examples of that in the class. It can also happen when a limit is approached or met or exceeded, and we saw that. Okay? And it doesn't always behave the way you think it would behave, right? We had a hypothesis about how it would behave, and then it behaved differently. All right, so let's talk about tools. Let's think we can automate some of this stuff. There's lots of tools out there in the world. Lots and lots of tools. Tons of tools. Too many tools, right? You get inundated with, everybody has a tool for you to use that will solve all your problems. So Microsoft provides some closed source tools, but they're free, and they're pretty good, actually. And they're there to help you with Windows development. One of them is App Verifier. That's a runtime verification tool for unmanaged code. What is unmanaged code? Well, I don't want to get into the .NET framework and all that stuff. Just for right now, just read that as code. And it assists in finding what they call subtle programming errors. And these can be security issues that have to do with account privilege problems, etc. And they're difficult to identify in normal testing of the application. And you can read about it there. And App Verifier, I believe by default, is on Windows. So you've got it on your Windows machine. you might as well use it. There's something called the kernel address sanitizer. It's a bug detection technology supported on Windows for kernel drivers. Right? If you're going to write some code that's going to run in the kernel, you'd like that to be good code. And you'd like, in particular, to be sure that it doesn't perform illegal memory accesses. What are those? Buffer overflows, use after free, double free, all the usual culprits that you're familiar with. And the kernel address sanitizer is a technology to help you with that. I don't think by default it's on there, but I think if you install the one of the development tools, install Visual Studio, I think you get that as part of that installation. There's a link to read more about it. Driver verifier, that monitors Windows kernel mode drivers and graphics drivers to detect illegal function calls or actions that might corrupt the system. So we're looking at a combination of static and now dynamic tools. Driver verifier can subject your driver to a variety of stresses, right? This is a dynamic tool. It's going to run your code and look for improper behavior while it does it. I think you have to download it, but it's free, and you can read about it at the link there. So good tools. What else is out there? Well, there's something called CPP Check. It's a static analysis tool for C and C++ code. Great. It provides some code analysis, lets us detect bugs, and tries to detect undefined behavior and dangerous coding constructs. And its goal is to have few false positives. What's a false positive? A false positive occurs, right, when I alert you and I say, hey, this is bad. And you go look at it and you say, no, it's not bad, you're wrong. That's a false positive. Right, a false negative where I say, your code's awesome. Go for it. Push the button. You push the button and it blows up. Whoops, that was a false negative, right? So I'm not going to talk about hypothesis testing and type 1 and type 2 errors, right? A false positive is basically noise. It's something that you have to deal with, but it's not really a problem. So they tried to minimize it. So, for example, I went out onto GitHub and I grabbed a repository and cloned it. And then, just for fun, I did a CPP check of their keylogger.c. And it immediately says, hey, I found an exit path from a function with a non-void return type that was missing a return statement. So that function ends with fclose, and then there's just no return value. So that's not good, right? The program has a non-void return type, like the function returns an int or something like that, but there's a path out of the function that doesn't return a value. What happens there? It also found this return value of allocation function fopen is not stored. What? The return value of the allocation function fopen. Oh, fopen is going to return something to us, and they never bothered to store that. That's not great. All right, so it found a couple of real issues. Those are things that we should be concerned about. Another tool is Flaw Finder. Flaw Finder is a little program that examines C and C++ source code, and it reports potential security weaknesses. And it tries to sort them by risk level. So again, I ran it on the same thing. I ran it on keylogger.c. I used the default rule set, and here it goes. And it says, hey, if format strings can be influenced by an attacker, they can be exploited. And it gives me the specific CWE for that. See, I like that, giving me the CWE. Use a constant for the format specification. So apparently what's happening is in the code, I'm building a format specifier, right? The second argument to fprintf, right? First one is the file stream. Second one is the format argument. I'm building that dynamically, potentially based on user input, and that could be a vulnerability. True. Good point. Then it says, check when opening files. Can an attacker redirect it, for example, by using symlinks or force the opening of special file types like device files? Can they move things around to create a race condition? For example, could your program be tricked into opening, for example, a device file? Could your program be a confused deputy? You should check for that. You should be sure that you're opening the kind of thing that you want to open. In addition, it says the same thing for another line. So it said it at line 8, says it again at line 10. So that's 2 cases where I'm using fopen and I should be more careful. Good to know that. And then at line 11, get char. Check buffer boundaries if used in a loop, including recursive loops. So it didn't find anything where we're checking the buffer boundary and it's like, hey, you might exceed a buffer here. You should check the length of the buffer. Okay, all this is good stuff. Notice it's completely different from what we got back from CPP check. We got back a couple things here. With flaw finder, we got back a different set of things. Okay, neat. There's also a tool called sparse. So sparse gives you a compiler front end, and it's able to parse C code. And it parses a lot of GCC extensions too. And a bunch of compiler backends. So the front end reads in the source code. The back end typically would be what would generate the RTL, which gets then translated into machine code, or maybe it generates machine code, right? It generates something. But in this case, the back end of it is not feeding out to an output file with machine code. It's feeding a static analyzer, and that static analyzer is also called sparse. It's great when you use sparse for multiple names. So, turns out sparse was created by Linus Torvalds, and he wrote it back in 2003. And he basically wanted to make Linux better. He wanted to be sure that people weren't mixing pointers to user address space, kernel address space. That's bad. And so it checks for those kinds of things. So we now run sparse over keylogger.c. I get a different set of results. It says incorrect type in initializer. We expected an int. We got an int star. That's bad. Symbol bin search was not declared. Should it be static? What's happening there? So I didn't find bin search. I didn't find a declaration for that. That may be because I just didn't include the .h file, but I didn't find a declaration for it. If it's meant to be accessed externally, there should be a declaration for it, like in a header file. If it's not meant to be accessed externally, if it's meant to be private to that module, it should be static, because static makes functions private to the containing module. So it should be one or the other. In this case, it seems that it's not doing either one, but it should. So maybe that's not an error, but that's certainly a concern, right? Maybe it should be static, and you shouldn't be able to access it outside the program, because that could be a vulnerability, okay? Incorrect type in argument 1, expected an int pointer, but I got an int. That's not good. And then non-size preserving pointer to integer cast. I got 3 of those. That's not great either. So those are all real concerns that I should look into and try to fix. That's it.